Yeah, welcome back. Global economics, and right now we want to do the econometrics. Still, we are in explaining the theory. So last time I started to discuss you what is a linear regression, and the linear regression is just that you make, so to speak, a hypothesis that you have some dependent variable, for example, profits, and profits are in general depending maybe on the number of employees you have in your company. This would be then X and profits would be Y. And you make the assumption that the more employees I have, the higher will be my profits maybe, and that you assume that you have a linear dependence between those two variables. And then you make just the assumption that you have to estimate the slope. So what would be the increase of my profit y if I increase my number of employees by 1? And of course, a linear line is defined by the slope and the cutting point of the vertical axis. And within our example here, I had some data of the not profit, but the sales volume and the number of visits of some representatives of your company, so to speak. Some guys who are knocking at the door of their neighbors and asking if they want to buy your product. Well, and if we have then this historical data, we can just plot the data. This would be the blue points here. And then just by a look on the data, we see, well, there could be something that the more visits, the more is my sales volume. And then I ask for something like, what would be the best fit for my data with an increasing linear line? And then we have to define what we understand by a best fit. And for this, we take the principle of variance that in general in statistics, we are talking about the fluctuation of data with the measure that we calculate the squared distance with respect to the mean, or in this case, with respect to the line I want to fit. Just one question, and I also want to write down here. So I have to take my laptop. Just a minute. Where is my... Did I close my slides? Back again. Okay. Here we are back again. So this works hopefully too. Yeah. So we are in the linear regression, and I want to explain what we understand by best fit in quotation marks of the data. And for this, we want to minimize the sum of all these red squares. So we are calculating for, in the beginning, for some linear line, all the distances of our data points, vertical distances of our data points with respect to our line. Then we square all these distances, summing these distances up, and we want to draw that line which minimizes the sum of all these squares. Let me put this like this. This is our aim. And for this, squared distances with respect to the fitted line. And well, one question. Have you talked within your introductory courses in statistics why we are taking the squared distance? Because of course we could also take the absolute value or we could take the fourth power, because sometimes it is only said that we want to cancel out the problem of plus and minus, and the square cancel this plus minus problem, so that the distance above our line or higher than the mean and lower than the mean, that they are valued always in the same way. Have you talked about, or maybe you know, why we are using very, very often in statistics the squared distance? The squared distance? Yeah, yeah, and yeah, that's definitely right. In the end, you have to look at your data, and especially in financial data, you quite often see that some other concept of taking the distance fits the data better. But on the other way, to taking the squared distance is still and will be still yeah, one of the main ways to take the to measure, so to speak, the volatility. And has he explained this? Okay, then the higher it is a higher value, so you are measuring because you are squaring, and if you have a distance of 4 and you're squaring it, then you take 16, and if you have only 1, then 1 squared is still 1. So the outliers, they get a higher value. That's true, but also then of course I could take the power of the fourth. And this so sometimes this is also meant as a reason. But well, behind this is a more philosophical reason maybe, and maybe you know how the normal distribution looks like. And the normal distribution, this is this Gaussian curve. And this curve you can describe with a function, and this function for the normal distribution, this is given by 1 over 2 pi square root times oops, sigma squared times x of x minus mu squared over sigma. And in describing the normal distribution, you have, in this case here, the squared distance of your data point with respect to the expectation value. And for the expectation value, we quite often take just the mean. And here you have this squared distance. Well, and hopefully within your statistics course, you have heard of the central limit theorem. Theorem. Do you know what this is? Of the central limit theorem of statistics? Okay, this means, well, in general, if we would know that our data is taken from a set which is normally distributed, then of course we have directly the reason why we use the square distances, because our distribution has within its description the square distance. But of course, very often we don't know what is the distribution of our underlying data. And then you can show, and this is the central limit theorem, that every, and this is very surprisingly, that every distribution will tend, or the expectation, the mean of your distribution when you're taking your data will tend in the limit to the normal distribution when you increase the number of your data. So, and this is a very powerful theorem, because this is what statistics is about. If I'm collecting enough data, then it will be always a good choice to take the normal distribution, because, of course, theoretically in the limit means if I go with a number to infinity. But if I have a large number, then it is a good choice to approximately assume that the mean of my data is normally distributed. And yeah, this is maybe in short the explanation why we so often just don't think anymore about taking just the variance, the squared distance for describing volatility. But on the other hand, my colleague was totally right. Of course, it would be also good to go deeper in your data in order to see if it is really a good approximation. So to speak, if I really have collected enough data to take the normal distribution as an approximation. Okay, so, but we are going back to our problem, and so we are minimizing the sum of these squared, so the total area of these squared should be minimized, and then we come to our fitted linear line, and this we have done in our example. Where did I? Here. So here we calculated the slope and the cut of the vertical axis. And of course, it could be the case, and this I showed you just here. It could be the case that the data is distributed, yeah, with a high volatility, like in this case, or it could be quite in the neighborhood of my um, fitted linear line. And I think at this point we were, because now we want to calculate the so-called correlation coefficient, or the coefficient of determination, in order to have an idea how, in quotation marks, good our data is fitted by our linear line. So, and I think at this point we were the last time. So here, when every data point is lying on the fitted line, then we have a correlation coefficient of r equals 1. And if we have, so to speak, no idea which would be the best line, then of course we have no correlation, and we would have a correlation coefficient of 0. And then I can ask you the question, within this data set, maybe this would be the best line. And you take the slide before here, then we can ask, where would we expect our correlation coefficient in this case? In the neighborhood of -1, in the neighborhood of 0, or in the neighborhood of 1? What would you think? Okay, great. So roughly in the neighborhood of 1, because we are quite close with our data points in the neighborhood of our linear line, and of course +1 because we have a positive dependence. And in the right case, and plus or minus positive. So you would then an increasing line just by eye. You would put an increasing line within this. Yes, I think so too. Maybe this one. And so then maybe roughly let's let's think of it minus 0.4. We will later on go into the data, and I gave you the data here. So this is the data for this, and this is the data for this. I think this is also my example from the linear regression we have already done. Okay, so, and then we want to calculate these coefficient of correlation, or the square is quite often taken also as a measure this, and this I think I also, yes, I also already explained to you last time because the coefficient of determination, the squared correlation coefficient, has this nice graphical interpretation that we can say if this is 0.75, then we can say from a descriptive standpoint that we are explaining with our data 75% of the dependence between y and x. But of course, then we have to keep in mind squaring a number means we have no information anymore about a positive or a negative dependence. But anyway, on the other way around, we directly see if we plot the data if we have fitted a positive or a negative line like in these two examples here. Okay, then. Oh, this is also the graphical description, how we can explain why we can interpret the coefficient of determination as the percentage of explaining our data, because let's take this example here. This one I plotted in the upper left side here, and then this is the fitted line, and this would be the mean of the data, the dotted line. This is just a y bar, sorry. And if you are describing a data set, then just calculating the arithmetic mean of your data is very, very often quite very often just the starting point in order to aggregate your data. And then, of course, your data is fluctuating around these arithmetic mean. And so to speak, if you are turning then, so to speak, this horizontal line, which is representing your mean, into the fitted line, then on average, your data points are fluctuating now not that much around this fitted line compared to your horizontal line representing the arithmetic mean. And that you move, so to speak, a bit more in the neighborhood to your data point. So from this long data to only this distance, this then we interpret as explaining the data. Well, and we have already talked about this. We are not taking just the absolute distance, we take the squared distance. So the interpretation we have to do then not just with the distances, but with the squared distances, which I plotted in the lower diagram. And then we can mathematically show, and maybe this you have done in your statistic course, that the total fluctuation measured via the squared distance of our data point with respect to the mean just splits in two squared sums, and the first sum is the squared distance between our data point and our hypothetical point lying on the fitted line. So these are the points lying on the fitted line. And then we take the next step and say we are calculating the square distances of the points of the fitted line, and now with respect to the arithmetic mean. And this is, of course, our data point. So for one point, this is the total squared distance. This one is the explained squared distance, and this one is the still not explained distance. And then also mathematically, we can show that the coefficient of determination is just these explained distance over the total squared sum of the squared distances. Okay, and this then with this formula, we will calculate also our coefficient of determination and our correlation coefficient. So this I can also copy, and then let's go into the next one. Oh, this is too large. This is nicer. So first of all, we have to calculate our theoretical y lying on our fitted line, and this we have already done here. So these are our two A's and B's, and let's again do it as an example. So the slope B was given as the slope. Oops. So first one y, and second one. Oops, this is too much. Oh, so again, there we have to have C and semicolon. Oops. Oh, the shift was on. Then the x values and still something wrong. So my syntax is, oh, C, there is a mistake. This has to be C3. Now this seems better. Yes. And again, our cut of the vertical axis is y values and x values. So then the data point lying on our curve is cutting vertical axis plus slope times our x value. So our fitted data point, so our hypothetical sales volume for 9 visits would be 21.72, and since I want to just copy this, I need some dollar signs here that I can copy this down. So these are now all our fitted data points, and now we need the square distance, which I did at first, hypothetical minus mean. Oh, this is the hut here. Yeah. So what we are calculating then is hypothetical value minus the mean. The mean I didn't calculate. This I will do just here. And then a squared. And we need also, in order to copy this, that we fix the mean. And then we need here the mean. And now we can copy all this down here. And then our data points with respect to the mean. So this would more or less represent our variance. Well, the variance if we would divide this by the number of our data points. But anyway, so this is then the data point itself minus the mean. This again we have to fix, and this I can do with F4. Maybe you know this also. This actually I learned, I think, around 10 years ago from some student. So, what else do we need? We need the sums of our squared distances. Going back here. So, sum of this and sum of this. And this is our explained, this is our unexplained data. So, r squared would be then, not unexplained total is 572, sorry, over 572. So this is our coefficient of determination, and then our r would be the root equals the root of this, and this would be 0.91. And yeah, of course, then we have also to look at our data. Let's plot this again. And then we see, okay, we have a positive dependence, so we can still take here the plus sign. In the other case, we would need to insert here a minus sign, and this we will do in a minute for these other example I gave you on the slide, on the former slide. Okay, then very surprisingly, we of course have also a formula for this, and in German this is Bestimmtheitsmaß, coefficient of determination, y data and x data. Enter is of course the same number, and I hope this correlation coefficient, and this one and this one. enter. Okay, well, and if you have done this, the nice little thing is copy. Let's take 5 here. I think I have the same number of data points in this example here. But unfortunately, this is a picture, so let's take this and put it just here. This I can do, or yeah. So I need 2, 3, 4, 5, 6, 7. This is nice. Equals this plus 1. And we have 24, 9, 18. 24, 9, 18, 8, 19, and 8. This we can remove. Here we have the same picture as you have it on the slides. Well, and everything else we have to do in the same way as before. And yeah, now we have a correlation coefficient here of minus. See this? Minus 4.6. And if you're taking just the square root, then of course now we have to insert here a minus sign in order to be right. Okay, and then this we will do then for our economical data. What you also can do is, I think I already showed this, clicking into the data and choosing trend line. This is here in order that you see this. Linear you choose, and we want to have our formulas. So show the formulas and show the coefficient of determination. And here we are, 0.84 you have them directly. And this we do also for the negative part. So clicking into the data, right click, choosing trend line, linear. Here you have to be careful because sometimes we take the log of our data. This you then don't have to do if you directly choose log, or quite often growth processes are quite often exponential processes. So with this you can play a little bit if you want. So then show the formula and show the coefficient of determination. And in order to have this, here we had 0.84. So this was done. R is 0.84, and in this case we had R equals minus 0.46. Okay, and now we are going back to economics, because what maybe I can also put the data inside here. this was this example, I think. Oh, this is not why this doesn't function. Is working? Yep, this is working. Great. And this was 0.91 and this was 0. Yeah, no, the other way around. 0.8 or what did I have? So squared 0.84 and this was 0.81 and this is of course 482.72 over 572. Yeah, and this as a summary is the interpretation of our coefficient of determination. This is a measure for the strength of the dependence, so to speak. How good is our linear fit with r squared is 0. We have no dependence, and with r squared is 1. We are lying with all our data points just on our line, so we are explaining. It is said here then 100%, and r squared can be interpreted as a proportion of the explained explained proportion by our linear regression. Yeah, and now we want to go to our economic data. If we are taking now Okun's law, and if we are going back here, how did it look like? Why have we done all this theoretical stuff? This was this here. Let's copy all this. Is this possible? Then let's do it like, boop, boop, boop. Can I do this in order just to cut this? Well, then let's do it like this one. Back. How do I get inside this formula here? So now it's possible. Now I can take the whole formula in order to copy it. Or let's take this one too. So, because if we are looking at the growth version of Okun's law, so the dependence between unemployment and real GDP growth, then we see that we also just have within here a linear hypothetical linear dependence between our two variables. So this is our data, and this would be then our slope, and this is the vertical cut. And what we want to do now is to make a linear regression between the change of unemployment and the GDP growth. And for this, at first, let's take US data back to Excel. And did I have this here? This is or let's take it maybe a new one because well, this since we are already 10 minutes past 9. Um, there is if you look also at the explanations for your term paper, there is one data bank from the Federal Reserve System, and this is from the Federal Reserve Bank of St. Louis. And here you find also many time series from all over the world. And also what you have is, and this you can maybe try at home. If you go there, then you have also an Excel plugin so that you directly can download the data within Excel. And if you go through these explanations here, then you can implement this plugin into your Excel program. And this, of course, I have already done. And if you have done it, then you can look up here real GDP US gross domestic product. And then you see here GDP C1. This is the shortcut for real gross domestic product in the US. And this you would put then here. All this you find also in the description. And what we also have is unemployment rate. And here you see the shortcut is UN rate. Oops, this is too large. This is the right format. And if you click then up here, if you have implemented the plugin, you will find it in your Excel program. And we want to have a frequency of, hopefully this works. Maybe my processor, since I'm streaming this, now it's coming. Yep, it takes a little time. quarterly data, and we want to select all in the list now and add frequencies, and then we can get data. And now we have our data for unemployment rate and real GDP. And what we want to have now is GDP growth rate with respect to the former quarter. So GDP QOQ growth rate, and we want to have the change in unemployment, but this is no monthly data here. Oops. Yes. So I don't know why he has chosen now monthly data. We need the same frequency. So let's change this in Q and get data again. I think I have to click on here. Now he has done it, yeah. So now you see here 1st of January, 4th of January that we have here also quarterly data. Well, what we also need is the change of our unemployment rate. This I take, oops, the DU. And then you have to be careful. Here we are starting at 1947, and here we are starting at 1948. So the first possible change where we have the two correlating data points is the 4th of the second quarter of 1948. So we are starting here then with this time date, and the growth rate would be then the second quarter of 48 in GDP, this one over the former quarter, and the growth rate is -1. And that we have this in percent, we multiply this with 100. Then also here we have to put this in. This is in percent, and this is also in percent. No, it's not there. Can I click in it? Oops. What happened there? T. Cannot write anymore in my Excel file. Oh, sorry. Something bad happened. This still functions. Oops, but somehow my program is not working anymore. This is live. So quite often closing and reopen just helps, hopefully. But I think it crashed because I cannot close it. I hope that it's saved, but anyhow, so and Let's reopen it. So here we are. Uh, Unfortunately, it hasn't saved it. This is not that nice. So I have totally redo all the downloading. Still not. This is working. So but I cannot. Now I have a new one. So this was GDPC1 and this was rate. Then I need the frequency. Quarterly. Selecting all and get data. Again, monthly, I don't know why. Refreshing data. Now I save it. Then starting at the second quarter. This was GDP QOQ in percent and the change in unemployment in percent and the growth rate is this over this minus 1 times 100 and the change in unemployment is second quarter 48 minus first quarter 48. So, and now we can go down to 2024. And here we are. Maybe this we can do a little bit another way. Oops. And I think the time series for GDP, yeah, here you see it, that we don't get a number for the last quarter, and the reason is that we do not have data for the third quarter, but we have data for the third quarter in the unemployment rate. So let's skip this one. And going back, let's have a look at our data. Taking it. There I have done something wrong. Oh, I added the date. This I shouldn't do. And again, this one we don't want. So skip it and Now let's have a look at the data. Here we are, this -8. Where does it come from? I think these two. And for this, you have to be also careful for your country. These are some outliers, and I think this will have be the case within Corona times, since we now have here quarterly data. And if you remember, during Corona, especially the growth rate really jumped up and down just following the epidemical waves. Let's see if I am right that this was Corona. Yeah, here you see it. These are the Corona times, and there you have these huge changes. A jump in the change of unemployment of 0.2 to 9, and a jump in growth rate of -1.4 to -7.2. Well, anyway, that's the data, and we have to deal with the data which we have. And if we want to make an estimation for our whole data set, then of course also we have to take all our data. And please be careful. Quite often then we just argue, well, let's skip the outliers. But then, well, in a descriptive way, you are allowed to skip outliers. But if you want to go deeper into your analysis and doing uh, doing statistics where you want to identify casualties, then you are not allowed to skip some data points because your assumption is that you are taking your data, for example, just out of a sample of normally distributed data. And of course, also the extreme cases are possible if you have a normal distribution. So, but anyway, what we nevertheless, although we have these corona data, is that if we roughly have a look at our data set, we also see that there is a more or less negative dependence between change of unemployment and our um, our growth rates. Well, let's look. This I always don't know which is which. So we have f is x and g is y. Okay, where's our diagram? There. So f is x. This is our growth rate. Then let's put this also. This is y. This would be du. And this would be dy over y, our growth rate. And now clicking into our data, trend line, showing our formulas, then means we are done with our linear regression, or what you also can do is taking just this data and this we will also do. So B, this is slope, and we had y is, or the vertical axis was our unemployment data, and the other one our growth rates. Minus 0.4. Hopefully this is the same. Let's check it. Yes, here we have also the minus 0.4. And then, of course, the same thing for the vertical axis. Then we interchange the slope with the vertical cut. This is A, and we take the coefficient of determination and interchanging the vertical cut with the coefficient of determination. And this is then R squared. So you can do it like this, or you can do it in the graphical representation. And this I will cut. And then let's put it here. So this is our regression. And since we are interested at this number, we have to be careful what we have fitted now. Fitted delta u. This is, so to speak, from our linear regression, our y equals a plus b, and this was our growth rate, g y. So we have not directly this number which we are interested in. What is over the whole time series compared to the time period when Okun has fitted his data. Remember, this was, I think, in 1962, and now we are 60 years later. So ya plus bx. So this number is our 0. minus 0.4. No, this is 0.36. Sorry. The A is this one, and this is the minus 0.36. And then, of course, in order to get to this exposition, we have to rewrite this, since we know now this is 0.37 and this is minus, minus 0.47. In order, what is it compared to this -2? We have to divide this exposition by b, that we then obtain 1 over b times du is now our gy plus a over b. So, and this we then can interpret as the growth rate of potential growth, and this we compare with the two. And let's do it. So what we need, a over b, and we need 1 over b. Let's go into our data set. So what we then need is 1 over b, and this is, oops, 1 over b, and we need, so, oh no, minus a over b for the potential growth. Oops, don't want the equality sign. Then I have to reformat this cell, I think. Sorry, this doesn't work, but it will work in a minute. Not standard, but text. And now I can remove this equality sign. Yep. So, and this would be then minus a over b. So minus 2.1 and 0.8. Minus 2.1. So 1 over b is minus 2.1. And what else do we have? 1 minus a over b. This was 0.8 roughly, I think, yeah, roughly 0.8. So, and this now we can interpret, and then we find, well, even over this long time period, we find for US data still roughly the same dependence as Okun has found it within the 1960s, because he found roughly 2, and we also find roughly 2. And what is, I think, quite interesting is we have here now, so to speak, a rough estimation for potential growth over these, yeah, how much do we have? We start in 1948. This is 50 years, so over 70 years, we have a potential growth rate of 0.1, which is maybe a bit surprising that the potential growth rate for the US over this long time period is that low. So potential growth rate. Okay, I do not have that much time left, but then we will just do the download of the data, and maybe for the next time you can already start to try to do what I have done here with the US data for the German data, and we are talking then about Germany next time. So, what do I want to do with you is now doing the time series analysis for Germany with a data set starting in the 1980s, because you will find for your country at the IMF data mapper also the data starting from 1980. If you don't find it, please just write me an email, then I will help you how you can get the data. Yeah, so there we have a link. Hopefully this is still valid. Let's see. Uh, Also a live session doesn't work. Why is it not working? I don't know. Wow. You still hear me? Okay, because I think my computer is now crashing. Hopefully I have saved all this. This doesn't look very well. So maybe I'm gone in a minute. I hope that my video is... So I'm stopping the video. Oh, no, it's back. Yes, okay. It took a while. Okay, here we are. So IMF data mapper, or if you just go to IMF data mapper in Google, then you will directly find this link. And here you find World Economic Outlook data and data sets. Then you choose World Economic Outlook data, and there you find real GDP growth. Clicking on this, and then you can can I choose Germany? I don't know. I just download all data, or here select country data. What happens? No, then at first I maybe have to choose here list. I don't know. Well, I just download total data, statistics B, lecture. This is GDP. Going back, and again World Economic Outlook, and where is it? Here, unemployment rate. And I also just take all data. Unemployment, and then let's open it. Oops. Oh, I put it in the statistics lecture. This is wrong. Here we are. Back to global economics lecture, and open it. Okay, and then we need unemployment. for Germany. Let's take here Germany and then the GDP growth rate and unemployment. And this is unemployment. Let's go to Germany. There we are. Take the data. Then you have to transpose it because you have horizontal data and we want to have vertical data. We only want the numbers. And GDP. Here we are. Germany. There we are. And also transpose data. Oops. And only the data. And the date starting at 1980, I think. Yes, I'm right. Also verbs. No, transpons values. And of course, you are going here a little bit further. So this one here you can skip because this is a forecast of the IMF. So please go only until 23 because this is then hard data. Well, and to the end for today. Oh, sorry. Here we have already the growth rates, but here we need the change of unemployment for our estimation. So we have to start at 1981, just these two, and going down. And since I directly want to copy this, let's do it like this. And then starting from 1981, this is the data we want to use. And then with this one, we want to do our regression. And here you directly see, well, if you take the whole period, well, we can somehow see that there is maybe a negative dependence, but then you also see, well, we won't find a very high correlation between unemployment and GDP growth rates. Well, and maybe you can directly think of why with this data set we do not find such a nice dependence compared with the US data set with quarterly data over this much longer time period. But this we will do then on Monday. Thank you very much for today.